Greetings and welcome to Distill It. So, in lecture 26, we started an introduction to boundary value problems. And as an example problem, we started solving a diffusion convection reaction problem. And we solved it using finite difference methods. One thing that I wanted to clarify was that when I started the problem, I said that we'll be considering it for a general order n. But what we actually did was we considered it just for a first order reaction. So the way we solved it, we considered a first order reaction, which is fine because for a general order reaction, we'll have to use F solve. So I will not cover that in this lecture or in the next few lectures. I will cover a more complicated version where we consider a general order, but let's not do that for now. So I'll just remove this order right now. So I'll just consider a first order reaction, and because that gives us a set of linear equations, and that is a lot easier to solve. Okay, so we had sort of come up with a matrix over here. So we had come up with the coefficient matrix, we had come up with the constant matrix, and the variables, which were concentration values at all points, were basically what we needed to solve for, right? And now we need to code this in Python. But before I try to physically do this problem, let's just do some more simplifications, right? So an important thing to note whenever solving problems like this is that it usually helps to non-dimensionalize your problem. Otherwise, you start coming up with issues in units, and there are problems in solving it further. So it's always a good idea to sort of non-dimensionalize the problem before going ahead and solving it. So when you talk about non-dimensionalization of a problem, you consider all the variables in the problem. So for example, in our problem, there are two variables. One is concentration and the other is Z. These are the two important variables. Everything else, D, V, K, all of these are parameters, right? So there are two variables, concentration and Z. So we are going to scale these variables by some relevant scales that are provided in the problem itself. So for example, Z can be scaled by the length of this pore itself, right? So we could define a non-dimensional variable, let's say Z bar, which could be Z over L. So now what you've done is you've non-dimensionalized your Z, right? Similarly, concentration can be scaled by Ca naught. So we can have Ca bar is equal to Ca over Ca naught. Now, how this helps is when we put all these values here in the equation, we get the equation over here as D Ca naught over L squared D squared Ca bar by dz bar squared. So in place of Z, we wrote Z bar times L. Similarly, in place of Ca, we wrote Ca bar times Ca naught. So that's how we got this parameter over here. Okay. And similarly, over here we get minus V Ca naught over L, okay, d Ca bar by d Z bar, right? And finally, plus K Ca naught times Ca bar equals to 0. So that becomes your equation. Okay. Now, one thing that you can do is you can remove concentration from all of these terms over here. So all you get is D by L squared, D squared Ca bar by dz bar squared minus V by L dCa bar by dz bar plus K Ca bar equals to 0. So this does look fine, but let's sort of try and simplify it even further. So let's just uh, multiply L squared by D both sides. So when we do that, we get D squared CA bar by DZ bar squared minus VL over D DCA bar by DZ bar, right? Plus KL squared by D CA bar is equal to 0. Now, this is a very useful equation over here. I'll tell you how. So, so over here, we have this parameter, which is VL over D, right? So, VL, the unit of this is meter squared per second. This over here is also meter squared per second. So, and if we, let's say, divide by length squared, so this can be written as V over L over D over L squared. And if we take a reciprocal of this, so this is just similar to writing L squared by D over L by V, right? These two are the same thing. So now L squared by D is known as a diffusion time scale. So this has a unit of time. So L square is meter squared. Diffusion coefficient has the unit of meter squared per second. So the numerator has a unit of seconds. So this is known as a diffusion time scale. Okay. And we have L over V, which again has the unit of time. So this is known as convection time scale. So time scales, so this is something that you will do a lot in transport, where you compare time scales. So diffusion time scale is basically basically it represents how fast something would diffuse, right? And convection time scale would convey how fast is something going to convect, how fast is it going to move because of convection. So if it is primarily moving because of diffusion, then the diffusion time scale is going to be lower compared to the convection time scale, because it would take lesser time to move through diffusion, right? And if it is if it is moving by convection primarily, then the convection time scale is going to be lower. Okay. Yes. So basically that's the idea. And the ratio of these two time scales is known as a Peckley number. So the ratio of diffusion time scale and the convection time scale is known as a Peckley number. Okay. So that is a useful information to keep in mind. And the second thing over here is KL squared by D, which is this parameter. Right? So KL squared by D can be written as once again L squared by D whole over 1 by K. Now remember, K is the K is the rate constant for a first order reaction, right? So for a first order reaction, the rate constant has a unit of second inverse. So this has a unit of second, right? And K represents how fast reaction is taking place. So this represents the reaction time scale. Okay. And L squared by D is once again the diffusion time scale. Right? It's the diffusion time scale. And the ratio of diffusion time scale to the reaction time scale is known as a Dam-Kohler number. So this is the Dam-Kohler number. Okay. So once again, this is used for comparing how fast is the diffusion taking place compared to reaction, right? So these two are the parameters that we brought our equation in terms of, and these both of them are dimensionless numbers. So that's a good way to write our equation. So finally now we can write the equation as d squared Ca bar by dz bar squared minus Peckley number times dCa bar by dz bar plus Dam Kohler number times Ca bar is equal to 0, right? So that became our equation. So now when we formulated the matrix, so we had all of these terms. So let's just try to see which term really needs to be changed. So when we formulate our equations, we see that the first derivative, the second derivative, which has this d, now has no coefficient. So the coefficient of the first derivative, which was this thing, we wrote as alpha, right? So that was just d by delta z squared, but now there is no d over here. So we'll just write it as alpha as 1 by delta z squared. Okay, so alpha after scaling is 1 by delta z squared. And by the way, delta z now, since we have scaled everything, so your z bar is actually going from 0 to 1. Therefore, delta z is now just 1 over n instead of L over n, as we had shown previously. Now, since the entire domain is between 0 and 1, so delta z is now going to be 1 over n. So that has sort of simplified our problem a little. Okay. So that's the idea. So we have 1 over delta z squared, and since delta z is 1 over n, so that just becomes n squared. Okay. So that works well. And then v over 2 delta z was the coefficient of the first derivative. So now the equation has this pe as the coefficient. So instead of velocity, you're now going to write it as pe over 2 delta z, right? That's beta. And once again, delta z is 1 over n. So you will write this as npe over 2, right? So that's beta. And other than that, we have a few terms where we have this k, which is the coefficient of the linear side here. So the coefficient over here, which now is the Dam Kohler number. So wherever you see a k, you actually replace that by a Dam Kohler number. Okay. So that is going to be the way you are going to write it. So this is Dam Kohler number, and I think there is some, Dam Kohler number, right? So the values of alpha and beta have changed. You've written Dam Kohler number somewhere and so on and so forth. And once again over here, in the constant matrix, there was only one thing that we had shown, because everything else was 0. There was just one. The first entry was alpha plus beta times Ca naught. But now since Ca naught has been scaled, so now this is actually an equation in Ca bar. So at the boundary, Ca bar at Z bar equals to 0 is just Ca naught by Ca naught, because you've scaled it by Ca naught. So that is just 1. So this value over here is just 1, right? And now your matrix is ready to be formulated. So hopefully this is clear to all of you. Please try this yourself. And if, let's say, you start getting confused, what you could do is you could start from this equation. You could start from this equation over here and follow the same steps that we followed in lecture 26 to formulate the matrix. And you will be able to come up with this matrix that we have gotten over here, right? In place of k, you'll see Dam Kohler number. Alpha and beta would be as shown over here. right? So you'll get all of that. So in case you are not following what we have done here, it would be a good exercise for you to go back to lecture 26 and follow the same steps that we did to reduce to sort of get the matrix, and instead of using the equation that we used in the beginning, it would be a good idea to start with this equation as the mother equation, and then you can use finite differences to formulate the matrix. Okay, but anyway, since I would not want to do that again, so let's just go ahead and try to code this out, and let's see how we can do that. So an important thing to deal with such problems is the fact that you have to realize that there's a pattern. Okay, there's a pattern when it comes to formulating these matrices. Okay, especially in this case, because it's a tridiagonal matrix, so it's actually very simple to formulate the matrix. So if you see row 0, so if I say that my rows are represented by I and my columns are represented by J. Okay, so if I say A, I, comma J, so AI, comma J would represent ith row and jth column, right? So this would represent ith row and jth column, right? So the boundaries that we have, so the boundaries that we have are the last row, which is this, and the first row, which is this, right? There are no other boundaries, right? So it's just the first and the last row that are the boundaries. Okay, so other than the first and the last row, which means other than I equals to 0 and other than I equals to -1, everything else is very generalizable. So let's see how. So when I is equal to 1, right, every element in the first row, the row I equals to 1, every element is 0 other than the 0th element, the first element, and the second element, right? So that means the only non-zero elements are AI, the ith row. So in the ith row, the only non-zero elements are I minus 1, I, and I plus 1. So the only non-zero elements are in these columns, I minus 1, I, and I plus 1. Similarly, you can check that for I equals to 2. So you see, the only non-zero elements are in over here, which is the first column, the second column, and the third column, right? So every other column, 0th, 4th, 5th, 6th, all of these columns are 0. So I minus 1, I, and I plus 1. Only these have a non-zero value. Everything else has a 0 value. And this holds true for all the elements other than the boundaries, right? So let's try to do that. Let's try to formulate this matrix using Python. So how would you do that? So let's see the size of this matrix, the tridiagonal matrix, as we had shown over here, is n plus 1 cross n plus 1, right? That's the size of the tridiagonal matrix, n plus 1 cross n plus 1, right? So yeah, so that means that this is going to have n plus 1 rows, right? So if you start from the okay, so let's start by initializing the matrix A. Okay, so how do we initialize the matrix A? I will just say A equals to np dot zeros and I'll give the shape of the matrix over here. So it is supposed to be an n plus 1 cross n plus 1 matrix. So n plus 1 comma n plus 1. Okay. That is the idea. So you've got this. After that, we are going to write the generalized term. So for I in range, now you don't want to consider the 0th row. So you have to start with 1, and then you have to stop at the last value. So the last value over here, so so technically I is equal to -1, but you cannot go ahead till -1 because it would not, the for loop would not really progress ahead. So the last value over here is just n, right? Because this is an n plus 1 cross n plus 1 matrix, and the row starts with the 0 index. So the last index is going to be n. So you don't want it to reach n. So you will just say this, right? Because it will cover everything from 1 till n minus 1. N would not be covered, right? And then you can say ai comma I minus 1 is this. Then ai comma I is this. ai comma I plus 1 is this. Now remember, whenever you have a tridiagonal matrix, whenever you have the kind of equations that we solved, any second order differential equation, if you're solving using finite differences, other than the boundaries, you'll always end up getting a tridiagonal matrix. And because of that, you can very, very easily say that this code holds for every case. Just the values, the alpha plus beta, alpha minus beta, whatever, these values could change, but the general way of formulating the A matrix without the borders is, without the boundaries, is this. So this is the procedure you would always follow to formulate the A matrix. In fact, even the boundaries can be followed the same way. It is just that you will have to give a depending on what your boundary conditions are, it is going to change. But in general, this is the procedure for formulating the matrix A, okay, using Python. So this is the most general procedure. Okay. Now let's move on to the boundary condition. So when we treat boundaries over here, so the boundaries are basically I equals to 0 and I equals to -1, which is in this case n, right? So these are the two boundaries. So let's see how can we treat boundaries. So now boundaries, it could be specific. So over here, we just have 0, 0 and 0, 1. So we could do that. So we could say a 0, 0 is some value, a 0, 1 is some value. And after that, once again, we could have a over here, we have a n comma, this is n minus 2, this is n minus 1, and this is n. So we could say a n comma n minus 2 is equal to -1, and a n comma n is equal to +1, right? So that is how you've treated the boundaries here. And let's now formulate the constant matrix. So we formulated the A matrix over here, right? Now let's formulate the constant matrix. So the vector B, that is basically what we are going to formulate now. So to formulate vector B, you just have to start with saying that it is np dot zeros, n plus 1 comma 1, right? And after that, because this is the size of the vector B over here, n plus 1 cross 1, right? So yeah, nb dot zeros, n plus 1 comma 1, And then in our case, we only have the 0th element, which is this, right? And that is just minus alpha plus beta, right? Right? So that holds for our case, right? That's how you formulate the B matrix. Sorry, the B vector. And even if the other boundary is something weird and you get a constant there, you can include that. So this is how you generally formulate the matrix, the coefficient matrix A, and the constant matrix B. All right. And now what you have to do is you have to solve AX equal to B. And for that, we have the inbuilt tool in NumPy, np dot linear algebra dot solve a comma b, right? And we'll store that in the vector x, right? So now that we know a general procedure, let's try to solve this for Python, right? Let's try to solve this using Python. So I've already imported the libraries for you all. Okay, now let's try to formulate the matrices over here. So let's start by initializing my A matrix. And before that, I have to define N, I have to define delta Z, I have to tell about Dam-Kohler number, I have to tell about Beckley number, which will give me my alpha. Let's call it small a. I'll get a beta, let's call it small b. Okay, actually, let's just call them alpha and beta, just to avoid any confusions, right? And yeah, and nothing else is needed for now, right? So dz, as we know, is 1 over n, right? And the Dam-Kohler number, let's just take both to be 1 for now, okay? And we had defined our alpha, right? So our alpha was n squared, right? So we'll just say that's n squared. And beta, we had said is equal to n times Beckley number by 2, right? So that is our beta, okay? And let's say we are going to do it for 100 points. So that's going to be the case. Now let's initialize the A matrix. So that's np dot zeros, n plus 1 cross n plus 1, right? And now let's go ahead and formulate the matrix in the general fashion. So we can start by saying for I in range 1 comma n, right? ai comma I minus 1. So this is the element towards the left, right? So there are 3 elements. So the leftmost element, which is alpha plus beta. Okay. Then we have ai comma I, which is Dam-Kohler number minus 2 times alpha. Right? And then we have ai comma I plus 1, which is the one towards the right. And that's just alpha minus beta. Okay. So that's the idea. And then that just formulates the A matrix in general. And then let's just treat boundaries here. So in boundaries, the thing that we have to take care of is a0 comma 0, a 0 comma 1, a n comma n minus 2, and a n comma n, right? So this was 1, this was minus 1, right? And the boundary was, yeah, the boundary was, so this is once again the leftmost thing. So that's the Dam-Kohler number minus 2 times alpha. And this is the right thing. So that's alpha minus beta, right? So now you formulate, this completes the A matrix, right? Now let's go ahead and try to formulate the constant matrix, the constant vector. So now we'll talk about the constant vector. So once again, B is equal to NP dot zeros, N plus 1 comma 1, right? And we'll say B0 in this case is minus alpha plus beta. Right? So that holds for us. And now remember, we have to now solve for X, which is the concentration array. So that's going to be NP dot linear algebra dot solve. And we are going to have A comma B over here, right? So that would solve our problem. So we have now, you see, this is the concentration array that we've got, right? So that's the thing. I think I have to change the sign of the Damkohler number for this to decrease, because since this is actually reacting, so yeah, I'll just show this to you. So since my system is actually reacting over here, because of that, this has to be negative. This has to be negative because my system is actually reacting. My A is reacting over time. So this is the sign was incorrect, right? So this has to be negative. Okay. So let's go back to our Python over here. So we have this as my X. And now remember, what we have is C1, C2, C3, C4 till Cn plus 1, which was the fictitious point. So all we want is the profile till n, because n plus 1 doesn't really exist. That's a fictitious point that we took, right? So because of that, when we are going to extract the concentrations, we are going to start with 0, and then let's see what we can do. So we have the concentrations are they are not going to start with 0, they are going to start with 1, right? And then we'll add everything else other than the last value, because that is Cn plus 1, right? So that is going to be I for I in range length x minus 1, because we don't have to go there. And this is going to be xi. And remember, the shape of x is this comma 1. So basically, this is how you extract that. And that gives you the concentration array, right? This is the concentration array. And now let's just plot that. So let's also prepare a z array. So that is going to be I for I in range. Let's not do that. Let's see, np dot line space start at 0, stop at 1, and you need n points. So n plus 1 points. So now let's plot plt dot plot z comma c and plt dot show. So now you see, this is the concentration profile over here. As you see over here, the reaction has stopped taking place because the flux over there is 0, right? Let's say the reaction is very, very slow, right? So If the reaction is very, very slow, that means your dam cooler number is going to be small. Actually, let's just assign limits to my y. So plt dot y lim 0, 1, just so that we are able to make good comparisons. So over here, you see that's how the concentration actually changes over time, right? The concentration profile is like this in Z, right? Now let's say the reaction is very slow, right? So in that case, the concentration is almost the same everywhere. Let's say the reaction is very, very fast. So now you see the concentration has decreased more rapidly, right? Compared to this case, right? Let's say you are reducing the velocity, or you are just saying that there is no velocity, absolutely no velocity. So it's now going to just diffuse. So this is going to be the case. Let's say we say that the convection is very, very high. So in that case, this is going to be the profile. So now you could play around with this and see how the different parameters, the two main parameters, Damkohl number and Peckley number, actually change how fast or how slow would or what would be the concentration profile throughout in the pellet, right? So that is the catalyst pore. So that is basically how you can go ahead and you can visualize these things. Let's say that it's only diffusion, so this is how it's going to take place, right? And let's say it's very, very slow. So now there is no reaction taking place. Let's take a very fast reaction. So over here itself it goes to 0, right? So this is how you can see what happens, how is the concentration really dependent on the various the dimensionless parameters, Damkohl number and Peckley number. So hopefully you are clear on this thing. I think you will be able to appreciate this problem a lot more if you have taken a course on transport phenomena. We will definitely do this, do more transport phenomena in our channel. But for now, we've not covered transport. So this is a very good problem in transport, the diffusion convection reaction model. But basically, this is the idea over here. So hopefully you will be able to solve this problem. Hopefully you will be able to do such problems yourself. I highly recommend looking at multiple second order ODEs that you come across in chemical engineering. If you already are in your third or fourth year and you have seen many such ODEs, you could definitely go through those problems. You could see how you could code them in Python. You could play around with the number of points over here. So for example, if you go to 1,000 points, this is how the profile looks. So it doesn't really change. If you go to just 10 points, it becomes more sort of weird. And you could just see how this changes over time and so on and how this changes with the change in Damkohl number, Peckley number, right? Let's say there is neither reaction nor diffusion taking place, so it's just empty. Nothing really happens, right? It's just 1 here and 0 everywhere else, right? So it's a very interesting problem to talk about. It's a very nice sort of a chemical engineering exercise. So I hope you will have fun with this tutorial. We'll try to get more tutorials, and we'll try to try to generalize this for an nth order reaction by using F-solve. So we'll talk about that in the further lectures. So hopefully you will enjoy with this. Thank you.